Okay, good morning. So let me start with the seventh session of this lecture. So last day we did quite very important things. I'll just give you a glimpse of it, and I'll take forward. So today this second topic of module one that will be over. So first topic was battery. We had seen different types of alternators, how they produce AC that we have seen. Last day during practical hour we had conducted 2 hours almost of very important session. So in that we have rectifier circuit. So simple rectifier, that is bridge rectifier and all, and three-phase bridge rectifier that we had seen. And there also we had seen that the neutral of star connected stator, that is producing almost 15% of energy, and that neutral point is taken, and whatever third harmonic is produced at the neutral point, that is also rectified, and we are actually adding 15% DC in the supply. So very important concepts were covered. Those who did not appear for those 2 hours of session last Friday, please cope up, because these are the concepts. If you are not attending lectures, it will be difficult for you to understand. So after after the voltage rectifiers, we entered the domain of voltage regulator. So today we'll complete the voltage regulator part plus some other different types of alternators we will see, and we'll conclude this second topic of module 1 today itself. So I have given the name of the topic as voltage regulator, but we will start with this complete internal alternator circuit, a very important concept, a very important question for exam for 10 marks. So very brief, in 2 minutes, I'll tell you what is all about. So this was explained in detail in the last day. So what we are finding is this is the stator. This is a three-phase stator of star type, and you can find there is a neutral point. So four wire, there's a three-phase four-wire system. So these are the three phases. This is R phase, Y phase, and B phase. So this is R, Y, B. They are coming here, and these are the six diodes, which is actually forming a bridge rectifier, and they are actually converting this AC produced by the three-phase alternator. So alternator is the three-phase generator, which is mainly used for generating all the power required inside the vehicle. So engine rotation is given to this three-phase alternator, and this three-phase alternator stator can be delta connected, can be star connected. Here it is star connected, and this star connected stator we are taking out four wires. So these three wires are for RYB phases, so they are rectified here, and the rectified DC is going to the battery and for other electrical needs of the vehicle. Now one thing very important, we found that this neutral should be at zero potential generally, but for three-phase stator what we are finding is this neutral point is also generating some kind of harmonics. So that is actually third harmonics. If the stator is producing 50 hertz frequency, then whatever frequency we find at this neutral point will be 150 hertz, and that also we are rectifying by this fourth bridge arm. So these are the two diodes, main diodes for third harmonic rectification, and it increases output by 15%. So these are the four arm rectifier, which is mainly rectifying the stator voltages, stator and neutral voltages, and this is given to the battery. So this is the main power source. So this stator is the main power source, and this is the rectified power which is going to the battery. This is not directly being regulated. What we are actually regulating is, now check this left side. This is called a half bridge rectifier. So there's a half wave rectifier, not half bridge. There's a half wave rectifier. The same supply from RYB is coming to this half wave rectifier, and this is going to the warning light. So here this is less DC because this is half wave rectified. So this half wave rectified thing is going to the warning light. Ignition is also connected in series with it. The same thing, half wave rectified DC is coming to, this is called as the field coil, or this is called as a rotor coil of the alternator. So alternator is having two coils. One is the rotor coil. So this rotor coil is also requiring some kind of electricity supply to produce the rotor magnetic field. So this rotor magnetic field is deriving the electricity from the stator supply as well. So stator supply is half wave rectified, and one part of it is going to the warning light, and this is in series with the ignition. If there is any problem with the power supply unit, warning light will glow and it will give us an indication that yes, there is a problem with the one power supply unit. And the other things in parallel, you can see this thing is coming to the alternator field. So field is producing the EMF, MMF. MMF is the magnetic force. So this is the coil which is carrying current and which is producing an electromagnetic rotor or magnetic field in the rotor. And in parallel with that is connected another current arm, and this is coming at the regulator. So you can see that by regulating the voltage, by regulating the rectified voltage from the half wave circuit, we are actually controlling the current flowing through the field of the alternator. This is a very important thing we have to understand. That is, by regulator, actually we are controlling the current flowing through the field or rotor coil of the alternator. So just by increasing or decreasing the rotor coil current, which is shown here, field winding. Field means it is creating this current whichever is given to the rotor winding of the alternator. This is creating a magnetic field. That's why this is called field winding. And through the brush and slip ring arrangement, the current is connected with the rotating rotor and magnet. Okay, so that's why direct connection is not possible. We have to connect this supply by means of a brush and slip ring. So this rotor field and regulator, you can see they are kind of connected in parallel. So we are going to see this circuit today. We are going to see this circuit today, what is there inside the regulator. So this is a very important concept you have to understand, that by regulator, actually we are controlling the magnetic field of the alternator. And by increasing or decreasing that magnetic field, we are controlling the output from the stator. So more and less is the current flowing through this magnetic coil, magnetic field coil of the alternator. More and less will be the power generated, that is the AC power generated by the stator. Okay, so how this rotor magnetic field current is being controlled, that circuit we will see today, and that circuit will be regulator circuit. So very fast, and there are a few more things. So this supply is rectified going to the battery. This supply half rectified is going to the warning light. This is also going to the ignition. We have checked. And this is the, so there are mainly two types of rectifier. This is the half wave rectifier, which is giving supply to the field. This is full wave rectifier, and this is a third harmony rectifier from the neutral. This is giving supply to the battery charging. Okay, and these are the diodes. These are the 8 bridge diodes which are not allowing any kind of current from the battery towards the stator or towards the alternator. Very important thing we have to remember, that these are the bridge batteries, bridge diodes which are stopping or which are not allowing any kind of current flowing from battery to the rectifier, battery to the stator. So no current should flow from the battery to the alternator. All the currents and supply should flow from the alternator towards the battery. At any condition, nothing should come from battery towards the stator of the alternator. So these are the blocking diodes which are blocking any kind of current flowing from the battery to the alternator. So this is all about this circuit. Just go through very fast. The complete internal circuit has 6 main diodes. So these are the 6 main diodes which are actually converting the RYB phase. So each phase is separated by 120 degree. They are being converted to DC by the 6 main diodes. So 3 positive diodes and 3 negative diodes. Then there is a stator phase half wave rectifier. So these 3 are the half wave rectifiers which are converting again the same stator voltage into some little bit less current wala DC. Okay, so some is going for the warning light, some is going for the rotor magnetic field, some is going for regulator. There are 2 main diodes for rectifying the third harmonics. So if the stator is producing X frequency, here this will be having 3X frequency. Okay, that is another thing. The voltage regulator is shown in the diagram. So this is the voltage regulator. So please prepare this question for 10 marks. This big diagram you have to prepare for 10 marks. The magnetic field excitation supply are connected in parallel. That means the supply which is connected to the supply which is connected to the rotor magnetic field, that is this one, and the warning light, they are actually in parallel. For any fault in the charging light, the WL glows. Any fault in the charging light, the warning line glows. And what is this W? This W is actually given for that rev count, that is revolution count. So this actually W is giving us directly how much is the frequency or how much is the voltage in the any one phase of the stator. And as this is a balanced stator, any one phase voltage, if we know how much is the frequency of the phase, other two phases also will be having the same voltage and same frequency. So this W or phase connection is for revolution count or rev count, or to determine how much is the frequency of the supplied or generated alternator output, because that frequency is a function of speed. So suddenly there is a change in the speed of the vehicle, the frequency of the stator output will change, and that will change the output DC which is connected to the battery. So every single thing is very much interconnected. It is more said that the typical wattage for a WL bulb is 2 watt. So this thing is having a 2 watt wattage. Many manufacturers connects a resistor in parallel with the WL bulb to assess the excitation and allow the operation even if the bulb blows. So blows means even if it goes off, even if it goes cut, then also if there is a parallel resistor with this, the supply of the ignition and other thing will be on. The charge warning light bulb is extinguished when the alternator is functioning. So this was the main part. So W is shown here. So this W is actually the uh, for rev count or for phase voltage and phase current. So many details are there. You can write pages on this. Please prepare this question. Now let us coming to the regulator part. This also was shown last day. This is a very important detail. Remember that is 14.2 plus minus 0.2 volt is the supply that is actually generated by the alternator. Okay, and that is coming and actually charging the 12 volt battery. So it can be 12, it can be 14 volt, or it can be 14.4 volt. That is a minimum and maximum value. So whatever prevent the vehicle battery from being overcharged, the regulated supply voltage should be kept below the gassing voltage of the lead acid battery. So if you are overcharging the battery, at that time more will be the gassing created, that will create the pressure on lead, and it should not happen. Okay, so more gassing should be prevented. So to prevent more gassing, overcharging inside the battery must be prevented. So this is the range, very important detail, many important figure you have to remember. So 14.2 plus minus 0.2 volt, this should be the battery charging voltage, and more number of batteries we charge, current capacity of this voltage source increases. So actually we charge two batteries of 12 volt each inside the battery, inside the vehicle, and we keep them in series. So actually we are getting total 24 volt supply, but not exactly directly 24 volt. We are getting two voltage sources, batteries of 12 volt each, and this 14.2 plus minus 0.2 volt source from the battery DC, that is this point is actually creating 14.2 plus minus 0.2 volt, and this thing is going and charging the battery. So accurate voltage control is vital with the ever increasing use of electronic systems inside the car. It has also enabled the wider use of sealed batteries, because more we are able to control the battery voltage, better will be the battery life. We will not have to do any kind of maintenance of the battery. Only thing is we have to control the or we have to regulate the supply that is charging the battery. That is the only requirement. In that case we can use sealed battery, maintenance free battery. So as the possibility of overcharging is minimal, gassing will be less. Two common regulators are shown here. So these are the common regulators. So inside this the circuit is there. So voltage regulation is a difficult task on vehicle, as engine speed and load on alternator is ever changing. So these are very critical issues we have to remember. I told you in the previous slide that as there is a ever change in load condition, there is continuous change in the speed of the vehicle. So regulation will be very difficult, because the source itself is varying very fast. Okay, that's why regulator is very much required. Alternator output voltage without regulation rises linearly with engine speed. We don't want that. Okay, alternator output is directly proportional to the magnetic and field strength, which in turn proportional to the field current. It is hence the task of the regulator to control this rotor magnetic field current in response to the alternator output voltage. So if we want to control the alternator output voltage, actually we are supposed to control the magnetic field of the alternator. Again I repeat, if we want to control the actual output from the alternator, we are supposed to control the magnetic field or the field current which is flowing through the rotor of the alternator. So that is the main job. And there's a flow chart, and flow chart is also talking about checking whether the supply voltage is 14.2 volt. If supply voltage is 14.2 volt or less, no problem, switch the rotor magnetic field on, and in that case just keep on charging and check alternator voltage. Is the rotor voltage over 14.2? No, that means you can switch on the magnetic field on. So whenever the supply voltage is less than 14.2, we have to start make the current flow to the through the magnetic field coil. Again, I'll repeat, when the 14.2 volt is less, that is the output of the rectified output of the alternator is less than 14.2, there is still scope of charging. So in that case, we can switch the rotor magnetic field on. So less than 14.2, switch on the current flowing through the magnetic field rotor. And if the voltage is greater than 14.2 volt, switch off any current flowing through the magnetic field rotor. So if you are having pen and paper, very short, you can write down what is the regulator action. So in regulator action, we do two things. We just check what is the output DC voltage after the rectification of alternator voltage. If that voltage is greater than 14.2, cut off any current flowing through the magnetic field rotor. If that voltage, that is rectified alternator voltage, is less than 14.2 volt, in that case we can make the rotor field or rotor magnetic field, rotor magnetic coil carry some current. So more than 14.2 volt output voltage, cut magnetic field current. Less than 14.2 volt, switch on the magnetic field current. This is in short what is called as regulation. But the regulator action has to be continuously changing, because the abrupt switching of the field current does not cause abrupt change in the output voltage due to very high inductance of the rotor field winding. So rotor field winding is a very heavy inductor. So very fast change of output voltage will not happen even if we are making higher current flow through the rotor field winding. So it takes some time to build up. Okay, so last day we had discussed what is a memory-less system and what is a with memory system. So whenever we are talking about inductor and capacitor, that thing is having some memory. Okay, that thing is having some delay in current buildup or voltage buildup. So very fast you have connected some current to the magnetic field coil of the alternator. Then and there, the voltage buildup will not happen at the alternator output because it's having a memory. It will be taking some time to build up the current change in the magnetic field coil. That in turn again will take some time to build up the voltage at the output of the alternator. So it has to be a very smart system, because there are whole switching process takes a few milliseconds, but the build-up process for the current and voltage in the coil, it takes some time. Okay, so just see, it's a very difficult scenario because speed is ever changing in the vehicle, because continuously we are varying the speed of the car. As soon as there is a variation in the speed of car, the frequency of the alternator changes, and as soon as there is a change in the speed of the car, there will be a variation in the output of the alternator. As soon as there is a change in the output of the alternator, there comes a need to regulate the supply and regulate the current flowing through the field coil of the alternator, and that does not happen very fast. That takes some time to build up. So all things are against us, okay, because oil is taking some time, speed is changing very abruptly, voltage produced by the alternator is changing very abruptly. But under all these conditions also, we have to produce a 14.2 volt or little greater 14.4 volt DC constantly to charge the battery. So this is the bigger problem of the regulator. So many regulators also incorporate some temperature compensation, because there will be huge temperature inside the engine. So that also will change the circuit parameter. So with voltage compensation, voltage regulation, there will be a temperature compensation as well. So this temperature compensation will allow higher charge rate in colder conditions and reduce the rate on hot conditions. So too much hot condition actually against the production of voltage by the alternator, and too much cold is also against the voltage production by the alternator. Okay, but in our country it is hot country, so generally the engine gets too much hot. So that's why there is a temperature compensation in the regulator that will add to the more charge generation by the regulator or by the alternator circuit. So this is the circuit which was already shown to you, because this is the field winding, which is nothing but the rotor supply, and the same supply actually is coming from the stator DC half wave rectified output. So one supply directly going to the alternator. Where it goes, I will show you in the next circuit, next slide. Okay, directly one supply is coming to the base of one transistor, which may be, I think, T2. Okay, so that thing is this supply, and this is the field winding. Actually, we are supposed to cut or start current flowing through this field winding by means of the regulator, depending on the input condition. So more is the input voltage here, we have to cut the supply from the field winding. Less is the field voltage here, we have to switch on the current flowing through the field winding. So this circuit is very important. This is another type, but generally we will be studying the first type here. So how the voltage regulator is incorporated in the supply or earth, ground or field connection, this is shown here. Okay. So let us see what kind of circuit is here. So current and voltage regulator, but current regulator is not required because alternator do not require any extra form of current regulation. We are mainly doing the voltage regulation. That is, this is the supply which is coming from the half wave 3-phase rectifiers. So if you remember, I'll go 3 slides back. If you remember this point, okay, so this point, whichever is coming here, one supply is going to the WL warning light, another point is coming to the field diodes. From the field diodes, it is coming to the regulator. So this point, if you remember, this point is shown here in the next slide like this. I'll show you. Okay, so that is this point. So from the half wave rectifier, the V rectifier is coming towards the regulator. So this is the field winding. We have to cut the supply through field winding when this V rectifier is very high, because V rectifier is trying to go beyond 14.4. we have to cut the field winding supply. Okay, and V rectifier is falling below 14 volt, we have to switch on the field supply so that rectifier is producing or so that the alternator is producing more voltage. So this is the agenda. I'll repeat again. If this V rectifier is more, means whatever output voltage produced from the stator output and rectified, if that voltage is more, greater than 14.4, at that time we have to cut the field winding voltage, or no current should be flowing through the field winding. Okay, because in that time we don't want the rotor to get more energized and produce more voltage, because voltage is already high. So cut the field winding, reduce the voltage produced by the alternator and rectifier combination. If this V rectifier is less, at that time make some current flow through this field winding so that more voltage will be produced by the alternator, and the battery will be getting 14.2 or 14.4 volt for charging. So what happens initially, I told you there is one current coming directly inside the alternator, that is this path. Okay, so initially what happens, so alternator do not require any extra form of current regulation if the output voltage is exceed the preset level. Okay, this in turn allows a limited current flow through the field winding, and hence a limit is set for the field strength. So mainly we are supposed to set the field strength. Field strength means magnetic field strength, and magnetic field strength is directly proportional to the current flowing through this field winding. So cut this field winding, alternator will produce less voltage. Switch on this field winding, alternator will produce more voltage. So it will in turn limit the maximum current of the alternator can produce. The problem with the mechanical regulator, so there is a mechanical regulator also. I'm not showing you that, I'm showing you only electrical regulator, and this will be asked in the exam. This is called Zener diode based electronic voltage regulator. So this is that Zener diode. This may be a 3.6, 6 point something volt Zener regulator, which is having the property that if this voltage is high, that means voltage at the cathode. So this is the cathode point, this is the anode point. What we find is if this voltage is high at the time, higher higher cathode voltage, so higher reverse bias will make this diode conduct in the reverse direction only. So I'll repeat, the voltage across R2, whatever is the voltage across R2 at this point, that is nothing but the cathode voltage of the Zener. And Zener is having a predefined reverse voltage. So if that voltage is attained at the time, this Zener will become forward by this Zener will become conducting range. So a preset value of this R2 R1. So this R2 R1 is nothing but a voltage divider circuit, and that is actually connected from this V rectifier. So what is the voltage across R2? It is V rectifier into R2 divided by R1 plus R2, and that voltage we have to set same as the cathode voltage of the Zener diode. So V rectifier is coming, getting divided across R1 and R2. So what is the voltage at this point, cathode of the Zener? It is V rectifier into R2 divided by R1 plus R2. And that voltage we have to set same as the Zener voltage of this Zener diode. So whenever that this voltage is higher, V rectifier into R2 divided by R1 plus R2, when this voltage is higher, this actually triggers this Zener diode switched on. Zener diodes keep on conducting current that makes the T1 conducting. And as soon as the T1 becomes conducting, then the base of this pull down and T2 will go into a off mode. So all those things I will show you shortly. Explanations I'll give you shortly. Just see what is happening. So the problem with the mechanical regulator is the wear of the contacts. So continuously, so there is a solenoid kind of a thing. There is a contact make or break. So what happens in case of mechanical regulator is that contact is made or broke very frequently. So there is a wear of that contact part. This has been overcome with the use of electronic regulator, which actually due to more accurate tolerances and much faster switching, this does not create any kind of spark. There is no wear and tear. Only because of electronic action, this thing is controlling the current flowing through the field winding. That is cutting the current flowing through the field winding for V rectifier high, or switching on the current flowing through the field winding if V rectifier less. Electronic regulators are now universal on modern cars. They are far superior, produce more stable output due to the compactness and vibration resistance of electronic regulators. They are now fitted almost universally on the alternators. Okay, so that means nowadays there are no mechanical kind of regulator. Every vehicle is connected alternator, and regulator is of electronic type with Zener diode, or maybe there are IC based regulator also. Okay, instead of Zener diode, we can connect more improved IC based voltage regulator, and that is actually controlling the current flowing through the field winding or rotor winding of the rotor of the alternator. So the key to the electronic voltage regulation is a Zener diode. This diode breaks down and conducts with a precise reverse bias voltage. So that voltage is nothing but V rectifier into R2 divided by R1 plus R2. So Zener diode acts as a over voltage sensing and regulating element in a voltage regulator. So this circuit will explain in detail what is happening. So when this transistor is on T2, so be very careful, when T2 is on, this V rectifier, field winding, T2 and ground. So you have to remember, when T2 is on, at that time current flowing through the field winding. This is the path. So when V rectifier is kind of 14.2 volt or high, at that time this voltage is coming and it is actually flowing through this T2 and it is flowing through the ground. So 14 to 14.2, this is the range when this how this T2 is getting turned on. If the supply is in between 14 to 14.2, at that time this is the path through which, through this R3, this base of T2 is getting some supply, and that is making the T2 forward bias. As soon as T2 is forward bias, this is the current flow path from the V rectifier to the field winding to switching transistor. So this is the first condition, that when the V rectifier voltage is in between 14 to 14.2, that means over voltage is not there. It is within the range 14 to 14.2. In that range, field winding should be conducting. Okay, so voltage is 14 to 14.2. This 14 to 14.2 voltage creates a voltage here R3, and this base is getting the supply. Transistor T2 is switched on. When transistor T2 is switched on, this V rectifier current through field winding flows through T2 and comes to the ground. And rotor magnetic field is getting supply, alternator is rotating, it is producing voltage, and more time field winding is connected, the alternator V rectifier will increase. Now when the V rectifier increases, what happens is this voltage, how much is this voltage? V rectifier into R2 divided by R1 plus R2. That voltage also will increase. So as soon as it goes beyond 14.2, suppose it becomes 14.4, at that time this voltage becomes higher. As soon as this voltage becomes higher, this Zener diode starts conducting. As soon as the Zener diode starts conducting, this T1 becomes T1 goes into a conducting region. As T1 goes into the conducting region, this T2 will be in switched off condition because this voltage is more too much voltage, and this voltage will go into off region. If this transistor goes into off region, then there is no path for this current to flow, and this current through field winding will be cut off. So I'll again repeat. Okay, let us just go through this. When alternator first increases its speed, its output is still below the preset level. That means this voltage is 14.2 to 14. T2 is now on by a feed through its base through the resistance R3. So when this voltage is between 14.2 to 14, through R3 base of T2 is given some voltage, and in this case this allows the full field current to flow through the field winding of T2. This increases the alternator output voltage and V rectifier. So this part I have told you initially, that V rectifier in between 14 to 14.2, supply is coming through R3 to the base of the T2. T2 is switched on. When T2 is on, at that time this junction, actually this is a conducting path, so this will be the path through which the current will flow. Field winding will get the full current to flow through the field winding of T2. This increases the alternator output and V rectifier. Now when this is on for longer time, V rectifier slowly will go towards 14.4. Then what happens when the preset voltage level is reached? So this V rectifier into R2 divided by R1 plus R2 is equal to Vz, for V rectifier is equal to 14.4 volt. So as soon as this voltage is high, this voltage divider voltage is high, Vz is high, that is cathode of Vz is high. So when the preset voltage is reached, the Zener diode will conduct. So as soon as this becomes 14.4, Zener diode will conduct. Resistor R1 and R2 is creating a voltage divider used to set the Zener voltage input at the cathode of the Zener diode. When Zener diode breaks down with VR2 set at a preset value, the transistor T1 gets switched on. So as soon as this thing is conducting, transistor T1 gets switched on with high base current, because this base current is flowing because Zener diode is now forward biased. It pulls the base of T2 down to the ground. So whenever this is shorted, actually this voltage becomes zero, because this emitter, base, collector, all this becomes short circuit. So whenever this voltage is high, this voltage Zener cathode voltage is high, transistor T1 is high. When transistor T1 is high, this emitter and collector are connected kind of to the ground. As soon as this transistor T1 is high, the base voltage of T2 is actually brought down to the ground. That means base voltage of T2 becomes zero. As soon as the base voltage of T2 becomes zero, T2 will be cut off. So that is what is said here. Once ZD breaks down with VR2 set at a preset value, transistor T1 gets switched on. As soon as transistor T1 is switched on with huge base current, it pulls the base of T2 down to the ground. And whenever the T2 base is pulled down to the ground, it causes the alternator V output to fall, because whenever T2 base is to the ground, T2 is off. Whenever T2 is off, this base rectifier field winding is not getting path to the ground. That means this thing is open circuit. When T2 is off, this is open circuit. In that case, V rectifier is not getting a path to come to the ground. So as soon as T1 is on, T2 becomes off. As soon as T2 becomes off, this field winding current is cut off. So first case, T2 was on, this thing was short circuited to the ground, V rectifier, field winding and ground. This was the current path. Whenever the voltage is, input voltage is greater than 14.2, this T1 becomes short circuited because Zener diode becomes shorted. T1 becomes goes into the total conducting region. There is a saturation region that pulls the T2 base down to the ground. T2 becomes off. When T2 becomes off, this field winding is off. So these three paragraphs are very important if you want to explain how this voltage regulator works. So this will cause the ZD to stop conducting. So whenever this thing is actually grounded, at that time ZD will automatically stop conducting, because already the voltage of the alternator has become less. Why voltage of the alternator becomes less? Because this field winding current was stopped. As soon as field winding current is stopped, the alternator field or rotor is not getting excitation. In that case, the alternator voltage drops. If alternator voltage drops, V rectifier becomes less. When V rectifier becomes less, rectifier by R1 plus R2, this voltage becomes less. That means the reverse voltage on the ZD Zener diode becomes less. So Zener diode will go into cutoff region. So this will cause, that is reduction in the voltage of the alternator output DC will cause the ZD to stop conducting, and T1 will switch off, and the transistor T1 will switch off automatically. And if transistor T1 is switching off, at the time T2 will be on automatically. If T2 is on, in that case again this path will be short circuited and V rectifier, field winding, ground. So rotor will get supply and field will get supply, and again the rotor will start conducting and rectifier voltage will keep on building up. So these 4 paragraphs are very important. Just keep on reading it 3 or 4 times, you'll understand. And there is a diode called D1. Okay, what is the job of D1? This is not explained. So D1 is there to absorb any kind of back EMF from the field winding. So there is an inductive field. So inductive field actually produces some back EMF. So that back EMF should not go from this side. So the back EMF should not actually disturb the alternator function. So that's why the conventional diode D1 is there to absorb the back EMF from the field winding, which may damage the other component. So this will actually absorb all the back EMF from the field winding of the rotor of the alternator. So this is actually the characteristic or functioning of the electronic voltage regulator. So the very important question of this topic. So one important question is that full big rectifier circuit. And second big question is explanation of this circuit. So you start preparing for these 2 questions. So electronic regulators can be made to sense either the battery voltage and the alternator output voltage, or a combination of both. So output of the battery, if it is increasing, that means alternator output is increasing. In that case, you have to cut the field winding. So either battery output or alternator output, anything can be an indication that alternator is producing more output voltage. We have to cut the field. And as soon as the battery output becomes less, alternator DC output becomes less, that is this V rectifier output. In that case, again, we have to switch on this field winding. So most systems in use at present tend to be machine sense that this offers some protection against over voltage in the event of alternator being driven with the battery disconnected. So battery disconnected operation of alternator is not actually proposed. So always the alternator and battery should be connected. But for some testing purpose, we can remove the battery and we can test the alternator performance. So this slide is very important. These 2 slides, previous slide, this is about electronic regulator. Current regulation is not required, only voltage regulation is required, and how exactly the voltage regulation is done is given in this circuit. So please go through this, and if you need some more explanation, you just tell me. We will be keeping another session and I'll explain this thing to you in detail to your satisfaction. But you just go through these things, and whatever paragraphs are there, you'll understand. So over voltage protection for alternator, why required? So over voltage protection is required in some applications in order to prevent the damage of other electronic component like battery. When an alternator is connected to a vehicle battery system, the voltage, even in the event of regulator failure, will not often exceed about 20 volt. Due to the low resistance of the swamping effect of the battery. So battery is not allowing the voltage to build up, but it might go up to 20 volt. That also can damage the other components. If an alternator is run with the battery disconnected, which is not recommended. Okay, remember, battery disconnected operation of alternator is not recommended, but just to test the alternator performance, sometime we can disconnect the battery and can run the alternator. Okay, so due to heavy Zener diode connected across the output of the WL or field diode will offer some protection. So these are some additional protections against the over voltage. So if the system voltage exceeds its breakdown voltage, it will conduct and cause the system voltage to be kept within the reasonable limit. So across the output of the WL, that is the warning light, or field diodes, so some another Zener is connected. So if the regulator voltage tries to increase beyond the limit, at the time those Zeners connected across WL, which is not shown in the diagram, okay, that will get triggered. So these are some other over voltage protections for the alternator. Now what I'll show you is some more different types of alternators. This will not be asked in the exam directly. So for exams, you can prepare up to this over voltage protection. There are some other different types of alternators and other things which I am showing you is here. So one is a monolithic circuit regulator, and this is a type of Bosch compact alternator. Very important, high performance. So you can check 20 to 70% more power than the conventional units, 15 to 35% better power to weight ratio. That means with very less weight, this is delivering quite high power. Maximum speed up to 20,000 RPM. Just imagine how much strong the alternator will be. Okay, so twin interior cooling fans. So we'll be seeing what is meant by cooling. So there is a water cooled alternator, there are air cooled alternator. So here actually air cooled, so cooling fans are there. Precision construction to reduce noise. Okay, so car definitely should give us as less noise as possible. So this is an alternator, Bosch compact alternator, which is giving us very less noise. And version available 70, 90 and up to 170 ampere. Okay, so these are the current ratings of the alternator. There is efficient alternators. Whatever efficient alternator we have seen just now, you can see this is the how the stator is produced. So I told you previously that initially the stator is produced in terms of a line or long length alternator, and then they are rotated and then they are made compact and made this kind of stator. So this is the alternator which is shown in the previous slide. This is called actually LIX alternator. You can see here this is from the Bosch, and this is actually the stator. Stator is produced like this initially, and you can see there are three phases which are output. So this is definitely a delta kind of alternator. Star kind of alternator has another line which is nothing but the neutral point. Okay, so this is the alternator, how it is produced. So this is the stator part and this is the stator, and inside that this is the rotor. You can see here. Okay, so this is the pulley connected here, the machine is connected here, generator, sorry, the engine is connected here, and here is nothing but the rotor. Okay, so rotor is compacted like this, and this is the casing. And I had shown you last day that on this casing itself, the rectifier and regulator circuits, all those things are mounted on this. So whatever three-phase output you are getting after this alternator, that will be produced AC and rectified DC, and that directly goes to the battery charging. So a combination of experience, modern development methods and innovative production process has enabled to achieve dramatic gains in the alternator performance compared to conventional models. 35% increase in the power density, 1.43 watt per cc. So this cc is nothing but the volume of the alternator. So per cc 1.43 watt is the output we are finding. A rise in maximum operating temperature, that means very high temperature, almost up to 120 degrees centigrade. Within that also alternator will be working fine. So increase in the maximum degree of efficiency up to 76%, from 72% we can achieve by using this alternator. So these are nothing but the details. Improved electrical configuration, optimized materials have enabled the manufacturers or engineers to increase the efficiency beyond 70%. Very big thing. Okay, the efficiency line generator or EL generators. This is a word you should remember what is meant by efficiency line or EL generators. So this is a very colloquial language they are using in the field of designing. So EL generators, so what is a full form? Efficiency line, that means high efficiency, almost 76% or greater than 70% it gives. It consequently need less mechanical power to generate the energy for the vehicle's electrical consumers. So this reduces the fuel requirements and therefore CO2 emission too. So increasing the efficiency is happening because of material. It is happening due to the electrical design. It is happening due to the reducing fuel requirement is reduced, and more output will be produced and carbon emission will be reduced. So all these are positive points of efficient line or EL generators. Remember them. So this is another EL generator construction. So you can see here it can produce about 10% more power compared to the other standard generators. Ideal speed is 1800 RPM, very important thing. So the demand for electricity in cars has been rising and rising and rising. So there was a graph I had shown you that compared to 2005, 2006, the increment has happened almost 5 to 6 times. So inside the car, whatever electronic things we use, whatever accessories, whatever comfort electrical systems, that is asking for more and more power. So this power requirement from the alternator is rising. Safety systems also is requiring power. Okay, so that's why alternator has to keep on delivering more and more and more power. And that's why this EL generator, very lightweight, high efficiency system with high less fuel consumption and high fuel efficiency ratio, all those things are there. So more attention is given to the efficiency of the generator with ultra efficient diodes, which are available as an option, and the efficiency of the new generator can be improved even up to 77%. Idle speed is 1800 rpm. EL produces about 10% more power. They are therefore an ideal component for the start stop systems. Okay, so highly changing input, very dynamic kind of input coming from the engine. Then also the alternator will be able to produce a very stable and less dangerous voltage, so it should not cross 14.4. That is a dangerous level. Okay, so less than that, very controlled, very regulated DC output will be produced from this overall system. Okay, so alternator, rectifier, regulator system, a very stable and regulated output will be produced. So as a consequence, the start of function can be used more frequently in this. So start stop means cutting off the field or again joining the magnetic field like this. So this in turn allows the most of the electricity to be generated in the coasting mode, which in turn means a fuel saving up to 2%. So this EL generator is actually doing the fuel saving almost up to 2%. So the EL series, efficient line series, is available in various sizes, covers a range of 130 to 210. The previous Bosch generator was generating up to 170. Now this is generating up to 130 to 210 ampere at 6000 rpm. This is the engine speed. Designed for especially quieter operation, and they can go almost up to 125 degrees centigrade. So just see the previous slide we had shown up to 120 degrees centigrade. Now this EL can be giving you 125 degrees centigrade. The previous alternators was producing maximum 170 ampere. This thing is producing 210 ampere. So these are some of the improvements in the EL. Water cooled alternator. So an interesting technique involves running the engine coolant through the alternator. So coolant is nothing but water here. So 120 to 190 ampere output range available. Cooling is actually increasing the efficiency of the alternator. Compared to the conventional air-cooled alternator, the performance of these new machines have been enhanced, more particularly in the following areas. So these are the improved efficiency, increased output, noise reduction. So 10 to 12 dB reduction in the noise. So 10 to 12 dB is the noise power reduction. Resistance to corrosion, machine is enclosed because it's a water cooled alternator. Resistance to high ambient temperature. So even at 130 degrees centigrade temperature inside the engine, this alternator will produce electricity very regulated, very stable, and very perfectly. So additional heating materials can be integrated into the alternator to form a system that donates at additional 2 to 3 kilowatt of the coolant, enabling the faster engine warm up after a cold start. So this thing is cooled by water, as well as whenever required a cold start, that means environmental temperature is very less at the time. There are some heaters which are actually heating up this water which is circulating through the engine, and this will actually add to the ease of the cold start method of the whole engine. So that facility is also provided here. So this contributes to reduction in pollution and increased the driver's comfort. So this is another high performance engine which is called as Denso high output alternator. You can check the current is going up to 220 ampere. Okay, so these are the things. These are alternate overall process. So whatever alternate was shown, you can see this is the stator, this is the rotor part, and these are called poles. Okay, so 1, 2, 3, 4, 5 poles you can check here. It is given here. So this is the pulley arrangement at the inside. So the alternate generator is connected here. Sorry, not generator. The engine is connected here through this bearing, through this gear things and all. It is connected to the alternator. And this side there will be the casing, and inside that there are rectifier diodes, slip ring bearing, and there will be electronic regulators. This is the rotor part. Okay, and this is the stator part. Okay, so rotor is this number 5, and stator is 100% testing for short circuit and insulation like this. And inside this there are the rectifiers and diodes. So this thing is fitted here. Okay. Slip ring, bearing shield, so they are here, art and no number. So you can check this diagram. So all these diagrams are given in Denton. If you want to see what is there inside the engine, how it looks like, you can check this. And I think this is the last slide for today. So I am finishing this second topic of module 1 today itself, and this is the last slide. If you want to get the full view of what is there, you can find it here. So this is that stator of the alternator. Alternator stator is this, and this is RYB supply. All these three are connected to this 6 full wave bridge rectifier, and they are producing the DC. And this thing is taken. So this thing is coming from the neutral point. So these two are that third harmonic rectifier. Okay, so these two are the third harmonic rectifier. This is a positive, this is a negative, and this 6 are the RYB phase rectifier, like this. And there is one connection going to the battery. You can check, this is the battery, it is connected, and from this point only it is coming to the electrical loads. Okay, so this battery actually will be giving supply to the DC loads of the whatever is in the vehicle. So this is that part, this side. One very important thing is the half wave rectifiers are not shown, which are actually giving supply to the field of the coil. So here there is a change. I will tell you, here the field of the coil is also taken from this full wave bridge rectifier. So in the previous diagram and this diagram, the difference is, previous case this RYB, they were rectified with a half wave rectifier, and that supply was going to the field. But in this case, the overall full wave bridge rectifier output is the DC, and that is actually going to the rectifier. So this is the regulator circuit, this is the regulator circuit, and this is that rotor field connection. So if this voltage is high, at that time rotor supply is disconnected by this regulator. If this voltage is low, at that time this regulator is connecting the rotor supply, and rotor is again giving the alternator a start, and alternator is producing more voltage. So this voltage high, rotor current cut, this voltage low, rotor current connected. And this is that regulator. Here this is not the Zener regulator, but here it is some other transistor based regulator. And this output is given to the warning light, and this is going to the ignition switch. So we start this process first. As soon as this thing is connected, alternator EMF, alternator field is getting some kind of supply. Stator is starting producing some electricity, and that is converted to DC and going to the battery. So from the left, ignition, warning light, then the supply comes to the rotor, and when rotor is getting some supply, stator is producing some output, and that supply is going to DC, and that supply is also coming to the electrical load. So this is the overall system or a charging system for any kind of vehicle. So there will be little changes, but more or less this is the basis of the charging system. So this overall system you should remember, who is charging where, what is the current flow, and other thing. So I am declaring the second topic of module 1. Next day we will start the next system. Okay, so that is the third topic it will be, and I think it is a power system and all, DC series motor and all these things we have to start. Okay, so any doubt you ask me. So the 6th and 7th lectures I'll be uploading today itself. Thank you.